Hello everybody. So today we're going to continue with section 3 of using Newton's laws in everyday events. So we've talked about car crashes and why we wear seat belts. Then we talked about free fall and how the acceleration in free fall on a planet doesn't depend on the mass of the object, but on the mass of the planet and how far you are from its center. In any case, because the mass of the object cancels out, that means the mass of the object has nothing to do with the acceleration in free fall. If you drop a marble and bowling ball at the same time, they hit the ground at the same time. However, we were looking at a different situation when we stopped last time, and that was the marble and the feather. We said the marble will hit the ground first and the feather later because of air resistance. Our planet has an atmosphere, and because of that, air resistance can affect the acceleration that gravity produces. So what we want to do is we want to see how that works. In air, the marble will accelerate straight down quickly and have a very large speed. But the feather will just waft around and make its way down. However, in a vacuum, they will both fall straight down and have the same speed when they hit the ground because there's no air resistance. So let's see how that works. Okay, so we're looking right here at the top of the second page of the notes. All right, so here's how it works. When you drop the marble and the feather, both of them have gravity pulling on them, like this. Okay, so here's the gravity pulling on each one. But the marble has only a little air resistance acting on it because it's very aerodynamic. It just pushes right through those air molecules, okay? On the other hand, the feather has a large air resistance compared to the ball, the marble. And because of that, it wafts around. Each of those little fronds on the feather catches the air molecules, and that is a resistance. And so it prevents the feather from having an acceleration due to gravity like the marble. Okay? On the moon, that would be different. On the moon, they would both have the same acceleration and hit the ground at the same time with the same speed because the moon has no atmosphere. All right, so that leads us to the questions, will objects in free fall accelerate all the way to the ground? Okay, in a vacuum, like on the moon, yes. In an atmosphere, like on Earth, no. Oh, really? You mean if I went up in a plane and chucked a bowling ball out of the window, it would not accelerate all the way down to the ground? No, actually, it wouldn't. Isn't that weird? Well, let's take a look at it. When an object is accelerating through an atmosphere, the air resistance gets bigger and bigger and bigger as the object falls faster and faster. Remember, we said air resistance increases with increased speed. All right, well, at some point, the air resistance, as it increases, look at this guy jumping from a helicopter. He has a gravity of 833 newtons acting on him. And as he falls, the air resistance acting on him, it starts out as 0, it gets bigger and bigger and bigger as he falls faster and faster. Now, when the air resistance becomes the same value as his weight, as his gravity, then the net force is 0. And when the net force is 0, according to Newton's first law, there's no acceleration. So now he's going to travel constant velocity the rest of the way down. In fact, whatever speed he's traveling, when the acceleration stops, when the net force becomes zero, that constant velocity has a special name. It's called terminal velocity. Terminal velocity. And it's the maximum speed reached by an object in free fall in an atmosphere. Now, if there's no atmosphere, the object will accelerate all the way to the surface, like on the moon. All right, because there's no air resistance to impede the progress of the falling object. No air resistance, you'll continue to accelerate because there's nothing to balance the gravity. No balance the gravity, no net force of zero, you'll continue to accelerate, okay? All right, now what about objects with different gravities, with different weights? All right, think about the bowling ball and the marble. Both of those are spheres, which means they're fairly aerodynamic. But would they have the same terminal velocity? Well, think about this. The weight or gravity of the bowling ball is much bigger than the weight or gravity of the marble. So when you drop them both from a great height, the marble, because it weighs less, will reach terminal velocity first because the air resistance doesn't have to get as big to balance the gravity of the marble. On the other hand, the bowling ball has much more gravity acting on it. So the air resistance has to get much bigger, and that's going to take longer to balance the gravity of the bowling ball. So since it takes longer, it reaches terminal velocity some point after the marble does, and its terminal velocity will be larger because it accelerated further before it stopped. Okay? So the takeaway from this would be objects with more mass, that is, and weight. All right? Remember, more mass means more weight, will reach terminal velocity there we go, I spelled it right. Terminal velocity after lighter objects. Okay? So objects with less mass and therefore less weight will reach terminal velocity first, and heavier objects with more mass and weight will reach terminal velocity later, and therefore they'll be traveling faster because they took longer accelerating. Okay? Now, here's a good question. Would objects have a terminal velocity on the moon? No. Because there is no atmosphere on the moon. Atmosphere. There we go. And since there's no atmosphere, guys, there's nothing to impede the acceleration. So there is no terminal velocity on the moon or on any planet that does not have an atmosphere. However, if it has an atmosphere, you can, if you fall far enough, reach terminal velocity when the air resistance on that planet, in that atmosphere, balances your weight, your gravity, and therefore stops the acceleration, okay? Now, this is going to be kind of cool. I think I'm going to blow your little minds here for a moment. Suppose you were skydiving. I don't know if any of you guys have ever been skydiving. I never have, because if God wanted me to jump out of an airplane, he'd given me wings, but he didn't. So I don't go skydiving. But how would a person feel in free fall? Well, a person in free fall, he would feel like he is weightless. He would feel like he's weightless. He would feel like there's no gravity on him at all. But does that mean he actually is weightless? Absolutely not. He is not weightless. Gravity, if you're on Earth, gravity is always acting on you. Here's the catch. When you're weightless, how does that work? A person feels weightless because you cannot feel Earth's gravity pulling on you at all. You're sitting in your chair at home watching this video. You actually are not feeling Earth pulling on you. You can't. People don't feel Earth pulling on them. So what is it that gives you your sense of heaviness? That's a good question, isn't it? What gives you your sense of heaviness, gives you your sense of weight? Well, it's actually called apparent weight because it seems like your weight. What you feel that seems like your weight and actually isn't is apparent weight. And it's actually the force acting on you from a surface. In this case, the seat of the chair pushing up on you that you're sitting in. That's the force that gives you your sense of weight because it's preventing you from accelerating in free fall towards the center of the earth. So, a person feels weightless in free fall because gravity is the only force acting on them in free fall. And since you can't feel that gravity, you feel weightless. You have to have a surface pushing on you to have a sense of weight. And in free fall, you don't have a surface pushing on you. So you feel weightless. Okay? Now look at these examples here. Here's a person in an elevator, a cute little person in an elevator. So let's take a look at this. When the person is in the elevator, if the elevator is at rest or maybe moving up and down at constant speed, then the normal force, or rather the surface force, I'm going to call it N, which is what we call your apparent weight. Your apparent weight and your true weight, your gravity, they equal. And because they equal, they balance out. Since your apparent weight and your true weight are the same size, you feel like you usually do because the surface pushing up on you is giving you a sense that you feel like you're this heavy, even though you can't feel this, but you can feel that and it's the same size. So you feel your regular heaviness when the elevator is at rest or moving up or down at constant speed. In other words, in equilibrium. And they balance. Now, let's suppose that you're accelerating up in the elevator, okay? When you're accelerating upward, like whether it's an elevator or not, it could be you're accelerating up in a jet airplane. It could be you're accelerating up the next hill on a roller coaster ride. It could be a number of things. But when you're accelerating up, in order to accelerate up, the force from the surface acting on you has to be much bigger because you want the net force to be up. So it's much bigger than your true weight. And since this is what you feel and this you can't feel, you feel heavier, okay? So right here, you're going to feel heavier when you're accelerating up. You feel heavier because what you feel, the apparent weight, is bigger than your true weight. Okay. Now, what if you're accelerating down? Whether it's in the elevator or on that first big hill on the roller coaster where you feel like you left your tummy behind, or taking a dive in a jet airplane. I've never done that, but I've always wanted to. I've always thought that would be kind of cool. In any case, to accelerate down, the bigger force has to point down. So now the gravity is the bigger force. Now remember, it's the same size as always. Your gravity, your weight doesn't change, but the surface pushing on you does. So now the force from the surface pushing on you is smaller than your true weight. And since this is what you feel lighter than you normally do, okay? So you feel lighter. All right? That's what you feel like when you go down that first big hill on the roller coaster. It's like, you feel like you're getting ready to come right out of your seat, don't you? Okay? And that's because the seat doesn't push up as hard on you as gravity pulls down. So you feel lighter than you usually do because this is what you feel and this is not. All right, now, what if you're in free fall in the elevator? Oh, look, the cable snapped. So now the only force acting on the elevator and the person inside is gravity. And because you're in free fall, there's no surface. The surface can't push up on you because it's accelerating under you as fast as you are accelerating towards it. So you can't catch up to it, more or less. You can't push down on it, in other words. So because of that, the only force acting on you now is gravity, and you feel weightless. There's nothing there to give you a sense of heaviness. Your apparent weight is 0, even though your true weight is not 0. Okay? All right, so that's pretty much the gravity stuff. All right, and I hope you all enjoyed that because that's kind of a blow your mind kind of little moment when you realize, oh, you don't feel gravity pulling on you. You feel the surface pushing up on you. That's what gives you your sense of heaviness, and that's kind of a new idea for a lot of you. So you need to wrap your minds around that. It's actually kind of cool, and we're going to watch some videos on that to help make it a little more clear. So I hope you enjoyed that. I'm always enjoying interesting things like this that kind of blow your mind. So you guys, I want you all to have a great spring break, okay? And stay safe, remember, all right? And have a fun time, but also stay healthy, all right? Watch your distancing. We'll see ya. Bye-bye.